So, have you ever stared at a function, something like y equals x cubed, and just wondered, what does it actually look like? I mean, really look like. Not just a few plotted points, but its actual shape. Where are the hills? Where are the valleys? How can we possibly know all that just by looking at the formula? Well, let's get into it, because calculus hands us this incredible tool to do exactly that.
Right, so this is our mission for this explainer. We are going to figure out how to sketch a curve's general shape without the tedious work of plotting point after point after point. We're going to become detectives, basically, using clues hidden inside a function's formula to uncover the secret shape of its graph. And you know what our number one clue is? The derivative.
The best way to think about the first derivative is, it's like a compass. It doesn't tell you your exact coordinates on a map, but it tells you which way you're headed. Is the function going up? Is it going down? The derivative always knows.
So this right here, this is the secret code. It's the core connection. Whenever the derivative, f prime of x, is a positive number, it means the original function is climbing uphill, it's increasing. And when that derivative is negative, the function's heading downhill, it's decreasing. It's really that simple. The sign of the derivative tells us the direction of the function.
Okay, so think about it. If we know when the function is going uphill and we know when it's going downhill, then we can pinpoint the exact spots where it changes direction, right? Those are the peaks and valleys of our graph. And the tool we use for that, it's called the first derivative test.
So this test, it zooms in on what we call critical points. Now, you should think of these as the hot spots. They are the only places where a function might switch from increasing to decreasing or from decreasing to increasing. And these points pop up where the derivative is either zero, meaning the slope is flat, or where it's undefined. And here's the logic. It's super intuitive. If our function is going uphill, positive derivative, and then all of a sudden it switches to going downhill, what have you just drawn? A peak, right? A local maximum. And on the flip side, if it's going downhill and then starts climbing up, you've just created a valley, a local minimum. The change in the sign totally reveals the shape.
All right, theory's great and all, but let's get our hands dirty. Let's put our new compass and our new test into action. We're going to open up our first case file and see how this all works in the real world with a classic cubic function.
Here we go. Keys file number 1. f of x equals x cubed minus 3x. Now what's the first step always? You got it. Find the derivative. A little power rule action gives us f prime of x equals 3x squared minus 3.
Okay, now to find our critical points, we take that derivative and we set it equal to 0. If we factor it out, it becomes 3 times x minus 1 times x plus 1. And that makes it super easy to see that the solutions are x equals positive 1 and negative 1. These two spots, these are our critical points. They are the only places a peak or a valley could possibly be hiding.
Now for the fun part. We build our sign map, which you see right here. We're testing the intervals around our critical points. So let's pick a number to the left of negative 1, say negative 2. Plug it into the derivative, we get a positive number. That tells us the function is increasing there. Now, in the middle, between negative 1 and 1, let's test 0. The derivative is negative, so the function is decreasing. And finally, let's pick something bigger than 1, like 2. The derivative is positive again, which means our function is back to increasing.
And just like that, the case is solved. At x equals negative 1, the derivative changes from positive to negative. That means the function went from increasing to decreasing, which creates a local maximum, a peak. Then at x equals 1, the sign flipped from negative to positive. That's a switch from decreasing to increasing, giving us a local minimum, a valley. We've just mapped out the basic shape of this curve.
That cubic function was a pretty nice warm-up, but the real power of this method, it shines when we start tackling more complicated functions. So let's level up. Let's look at a couple of cases that have some interesting little traps we need to watch out for. All right, next up, a rational function. The method is exactly the same, don't worry. Find the derivative, find the critical points, test the signs. But whenever you see fractions, you got to be a little extra careful. So before I show you the next slide, just take a look at that function for a second. What's different about it? Where could a potential problem, a little trap, be hiding? Aha! And here's the trap. It turns out there are actually two kinds of critical points. We still have the ones where the derivative is 0, which happens here at x equals 0 and x equals 2. But we also have a critical point where the derivative is undefined. And that happens whenever the denominator is 0, which is at x equals 1. In this case, that creates a vertical asymptote, a total break in the graph, but we absolutely have to include it on our sign map. It's a critical point. Okay,
Let's do one more, an exponential function. Now this one's going to need the product rule to find the derivative, but there's a really cool little trick that's going to make analyzing it way simpler than it looks.
So after we do the product rule, we find that the derivative is e to the minus x all times the quantity 1 minus x. Now here is the absolute key insight. That little term, e to the minus x, it can get insanely close to 0, but it can never, ever be 0. And it can never be negative. It is always a positive number.
So what does that mean? Well, since e to the minus x is always positive, it doesn't actually affect the sign of our derivative at all. The sign is determined entirely by that simple 1 minus x part. This means our only critical point is when 1 minus x equals 0, which is just at x equals 1. A super quick test shows the derivative is positive before 1 and negative after it, giving us a local maximum. See how that one insight made the whole problem fall apart?
Wow, we've covered a ton of ground here, from the basic ideas to some pretty tricky examples. So let's just boil it all down and consolidate everything we've learned into one final checklist of clues you can use for sketching any graph. And here it is. This is your game plan, your detective's checklist. The sign of the derivative is your compass. It tells you direction. Find your critical points. Remember, both kinds, where it's 0 or undefined. Use those points to build a sign map by testing the intervals around them. And finally, just read the map. Interpret the sign changes to find your peaks and valleys. That is the first derivative test in a nutshell.
You know, we've done some pretty fantastic work here. We can now find where any function is going up, where it's going down, and where its peaks and valleys are. But there's still one more piece to the puzzle, isn't there? In any of those increasing or decreasing sections, how is the curve actually curved? Is it shaped like a cup holding water, or is it spilling water? Is it smiling, or is it frowning? Well, that property is called concavity. And figuring that out, well, that's a job for the second derivative.